We'll finish up these problems. All right. So let's see, we finished off with this question here. And first question is there a change in the carbon skeleton as we go from this alkane to this alcohol? Any change in the carbon skeleton here? No, we're going from a compound that has 6 carbons to another compound that has 6 carbons. Okay, so we've eliminated anything there. The next thing I would say, let's try a little bit of retrosynthesis. We could do a couple of things here. We could do a retrosynthesis, and we could say, what's the first step? I mean, both of those questions. Could anybody tell me what the first step has to be? Right, absolutely. The first step has to be bromine and light, right, which will give us the tertiary alkyl bromide, like this. And then if we just focus on the retrosynthesis for 1 second, going backwards, what's the only way that we can make this alcohol? Would it be the Markovnikov addition of water or anti-Markovnikov addition of water? It would be anti, right? That's the only way we could do that. And so we would have to have this alkene. And so the question becomes, can I get from here to here? If I want to make this Hoffman alkene, would I use a hindered base or a non-hindered base? Absolutely, I'd use a hindered base. And so let's try treating it with potassium T-butoxide, like that. And that's going to give me the desired alkene, like that. That's not very pretty. Anyhow, that's worse. All right, there we go. And if we want to make this alcohol, all we have to do is an anti-Markovnikov addition of water. Who remembers the first step of the anti-Markovnikov addition of water? Anybody remember? Exactly. Yeah, you got both steps. You have borane and THF, followed by hydrogen peroxide and sodium hydroxide. And there you have it, my friends. That's it. That's the whole synthesis. Okay, let's try one more. So let's say we want to do this synthesis here. We're starting it with a compound that has 5 carbons. And we have a new compound that has 5 carbons. And so, you know, the very first thing is we could kind of do a retrosynthesis on this. If I'm not adding any new carbons to the molecule, what's the only possibility for the last step? What would the starting material be for the very last step? It has to be a what? What kind of compound? A dihalide, exactly. So like Tiana says, you'd have to start with, or have to have this in your last step. You have to have this dihalide. Okay, let me ask you another question then. What has to be the first step? Only possibility. Absolutely, bromine and light. So we'll put that in here, bromine and light. And so that's going to give us this compound. But somehow we're going to have to make, we've got to make this alkene, right? So we're going to have to move this bromine from the carbon in yellow over to the carbon in red. And in order to do that, we are going to have to do an elimination. So the first elimination we're going to have to do is going to be a Zaitsev elimination. So we're going to use an unhindered base, and that's going to give us the Zaitsev product. So let me draw a double bond here. And then in order to get to that Hoffman product in blue, we're going to have to do an anti-Markovnikov addition of HBr using peroxides, which is going to give us this compound. And then in order to get to the compound in blue, we're going to use a hindered base. And that could be DBU, it could be DBN, it could be T-butoxide, like this. And so to get from the compound in blue to the compound in red, I just need bromine. And then to cut to the compound in red, to the final compound, it's a 2-step process. First step is excess sodium amide. And the second step is going to be water. So you can see that this is quite a few steps. Step number 1 is bromine and light. Step number 2 is sodium ethoxide. 3 is HBr and organic peroxides. Step 4 is a hindered base, like potassium T-butoxide. Step 5 is bromine. Step 6, I'm running out of space here. Step 6 is going to be excess sodium amide. Step 7 is going to be water. So that's a 7-step synthesis to affect this transformation. Later on in this course, and in not too long, we're going to see syntheses that are up to 10 steps. And so again, you have to be very solid on your retrosynthesis and all of the reactions. And just to put the bug in your ear, in chapter 12, we're going to learn a bunch of new reactions, some oxidation and reductions and things of that nature. So the very last section, or the last 2 sections, I should say, in chapter 11, the first one is green chemistry. I don't spend a lot of time on green chemistry. You can borderline skip this. But the idea is that in 2023, scientists are always looking for ways to do chemistry in a green fashion. And that means that we want to prevent waste. We want to use less hazardous substances. So avoid things like chlorinated solvents, safer solvents, like I said, and maximize atom economy. Maximizing atom economy just means we want as little atoms that we're using to end up in the waste as possible. And so if you look at these 2 reactions that I have shown here, they're both simply Markovnikov additions of water across a double bond. It's the same reaction. However, if you look at the first one, you can see there's all kinds of atoms that don't end up in the final product, and they actually end up in the waste. Whereas if you use just acid catalyzed hydration as opposed to oxymercuration, demercuration, we have way less atoms that end up in the garbage. And so it's much better for the environment to avoid having all these atoms ending up in the waste. Another thing we like to do is use catalysts because they can be recycled and they prevent the use of stoichiometric amounts. Of course, if we can do a reaction at room temperature as opposed to heating it, that saves electricity, and of course that's better for the environment. And then renewable feedstocks, that's also a good thing because if we can have some kind of renewable source of our starting material, it avoids having to use petroleum products. All right, so when it comes down to increasing your proficiency in synthesis, the first thing, like I said, is always look at the number of carbons. Are we changing the carbon skeleton? And then look at the functional groups. As you learn more reactions throughout this course, you're going to have to add them to your toolbox, so to speak. And so you can make your own synthesis problems. I would say it's a very small percentage of my students that do this, but you can do it if you want to try. You can start it with something simple and then just keep doing reaction after reaction to it. And then you basically take away all the reagents and you could ask a classmate to do that. I don't force my students to do that in any way, shape, or form, but it's something that you might want to try if you feel led to do so. So that covers all of chapter 11.